story begins with one person. Well, not really all of that person. It begins with a single one of their cells. It can be a cell of the skin or blood or many other parts of their body. But this cell, taken from its home in living tissue, what we call in vivo, can be kept alive and grown in a dish in a lab, what we call in vitro. This is a fully specialized or adult cell. It has one job and it knows how to do it well, like a neuron carrying information, or your skin cells protecting you from the outside world. But we can do something to this cell that can turn back the clock. By introducing a set of instructions that are associated with the very earliest stages of human development, this singularly specialized adult cell can become a cell with near endless potential possibilities. We call this an induced pluripotent stem cell, iPSC for short. A pluripotent stem cell has the potential to become any type of cell in the body. These cells also can multiply and multiply and multiply, until we easily have enough that we can divide it among labs and scientists all across Europe, which is what we did. Each of these labs were interested in a different part of the body. Using their expert knowledge, they gave these cells instructions to guide and transform them into cells with the specialized characteristics and functions of the cells in the part of the body they were interested in studying. We call these cell models. From this shared batch of iPS cells, kidney models were made in the Netherlands, lungs were made in the UK, brain models were made in Switzerland and Hungary, with liver models being made in Belgium, and endothelial cell models, the cells that make up the blood vessels, were made in Austria and France. But why are we doing this? Other than the fact that it's really cool, of course. Well, on a daily basis, we are exposed to thousands of chemicals. Most of them are harmless in the amount we normally encounter them, but some can be pretty nasty. In the old days, it was trial and error to find out if something was toxic to us, but these days there are less people who are willing to volunteer for that. For some time, scientists have used animals to test if something is toxic in certain amounts, but in recent times, we have made a huge effort to reduce the number of animals we use for such testing, both for ethical reasons and for the simple fact that these animals are not humans, and what's good and bad for them is not always necessarily good or bad for us. So, we made our models, made with human-induced pluripotent stem cells, to test the potential toxicity of these chemicals on the different organs of the body. We wanted our models to be something that could be used instead of animals to predict whether or not a chemical would be harmful to us. But in order to know if our models would be any good at predicting toxicity for an unknown chemical, we first had to see if they could predict it for a well-studied one. So we put together a box of well-known chemicals and nanoparticles, each one known to be deadly to one of the organs we wanted to investigate. Then we took our beautiful cell models that we'd spent weeks, maybe even months making them, and we poured all these harmful compounds all over them. In the aftermath, we checked on our poor cells to see if they could tell us anything about what the chemicals had done to them. And, after analyzing, it turned out they had a lot to say. To make sense of all this information we're getting from our models, the lab scientists needed some help. And this came from the computational biologists and chemists. To translate this information, they built a range of in silico, which means in the computer, tools and methods to examine the data in different ways. First things first, all this data that had been produced in different models by different labs and different formats needed to be harmonized, standardized, and stored in a cloud database to make it more easily accessible and usable by everybody. This more organized data could then be cleaned up using different methods of quality control so it could be further analyzed. From this point, the data was looked at from several perspectives. Some researchers looked at this data to find patterns between the structures of the chemicals and their effects on the cells. Others used it to train predictive tools that could tell us about the effects of new chemicals with similar structures that haven't even been tested yet. One type of information we get are called dose-effect relationships, meaning what concentrations added to the in vitro models cause a certain toxic effect. If, as the old saying goes, the dose makes the poison, then the ability of these models to accurately represent the dose-effect relationships is very important. However, the doses obtained in our admittedly simpler in vitro models cannot be directly compared to what happens when we are exposed as a whole organism. When we ingest or inhale a chemical, some of it is absorbed, distributed across the different organs of the body where it can be metabolized, and then it's finally excreted, often as pee. Computational models that simulate this process, so-called pharmacokinetic models, can be used to extrapolate the effects of these doses in vitro to the respective concentration in the body parts that they would have in vivo. Then we can determine what doses that a human would need to be exposed to see the same effects that we observe in our in vitro cell models. An adverse outcome pathway, or AOP, is a tool to organize all this knowledge we've gathered into a series of building blocks that can describe how an exposure to a chemical can impact across various biological levels to produce an adverse or damaging effect. Imagine a chemical that binds to a protein and induces an effect originally at the molecular level, but that will go on to impact at the cellular, tissue, organ, and even whole body level. It's like a chain reaction that leads to the negative outcomes we see with toxin exposure. By linking these pharmacokinetic and other in silico models that we've made into an AOP, we can make an integrative data analysis pipeline, giving us a wealth of information that can be used to predict the impact of many chemicals might have across the whole body. And we're getting more and more of this information every day as our cell models are becoming more refined and producing higher quality data that can make better computational models, which can in turn suggest more improvements back in the lab. With the sharing and integrative cycle between in vitro and in silico scientists helping us both improve and achieve more than we ever have before. And all of this started with one cell taken from one person with endless possibilities.